interrupt and ask me. Okay. So the Zoom was not being recorded so far. Now it's being recorded. Thankfully, I have not done anything new yet. So that's all good. We are recapturing the heat capacity versus temperature. So for Einstein, there is a delta function. And Debye says that the heat capacity goes as a parabola until a certain cutoff, omega d. So for Einstein, there is a value omega e. And for Debye, there is g of omega d by g of omega is equal to something proportional to omega square for omega less than equal to omega d, 0 otherwise. And this proportionality constant can be calculated. It comes from the elastic theory of solids. I can refer you to material if you're interested in studying. So it happens to be 3 multiplied by the volume of the solid divided by 2 pi square divided by speed of sound in that solid, Cs whole cube. It's some constant, okay? So we are not going to care about it. It's some constant. So why does Debye have a cutoff? Debye says that the frequency, so I really can't be sure why did Debye take a cutoff. I don't know him. Why did Debye take a cutoff? But I think this was his rationale. So frequency is proportional to 1 over wavelength, generally speaking, for any wave, right? As things are moving. And Debye's idea was that there is a minimum lattice wavelength that exists in any crystalline solid. This wavelength is equal to the lattice spacing between atoms. So you have a minimum wavelength at which atoms can undergo vibrations. And if you have a minimum wavelength, since omega, the frequency is 1 over wavelength, you have a maximum frequency. That's why Debye took this cutoff. And also remember last time we did that for any g of omega, if you do 0 to infinity g of omega d omega, this should come to be equal to 3n. Okay, so let's call this equation 2, and let's call Debye's expression over here as equation 1. So we are going to work with this using our equation for ln q. We can do one more thing. We can take equation 2 and put it in equation 1. So equation 1 says that g of omega is 3v divided by this thing multiplied by omega square. So if you do that, you get 0 infinity 3v 2 pi square cs cube omega square d omega is equal to 3n. Notice that now this integral won't be going to infinity because Debye's thing cuts off at omega d. If it was going till infinity, then of course it would diverge. So from this, you can get the Debye frequency, omega Debye, by doing this integral comes out to be speed of sound multiplied by 6 pi square n by v to the power 1 by 3. And if you are paying attention, then n by v is the density of the material. So that's what we get for Debye. So this is all the preliminary for the Debye stuff. Now we will get into the actual StatMech and compute our ln q. So we showed last time that ln q is equal to minus 0 to infinity d of omega, g of omega, ln e to the power beta h cut omega by 2 minus e to the power minus beta h cut omega by 2. This can be simplified as minus 0 to infinity d of omega. This is general. This has nothing to do with Einstein Debye or anything. This could be for any arbitrary model of g of omega. ln of e to the power beta h cut omega by 2 1 minus e to the power minus beta h cut omega. Okay, I have just simplified the algebra. This then becomes ln of e to the power beta h cut omega by 2. That is ln and e, they cancel out. So you are left with minus 0 to infinity d of omega, g of omega, e goes away. So we are left with beta h cut omega by 2 minus 0 to infinity d of omega, g of omega, ln 1 minus e to the power minus beta h cut omega. So what we are going to do today is basically a bunch of algebra, but it's still important because it shows you the process of how you work through everything. Okay, so this is our equation number 4. This is the expression for ln q. Any questions about this? It's just algebra and you are all masters of algebra, so I imagine there are no questions. Okay, great. So what do we need? We need CV. CV can be calculated in many ways. You can do T partial S by partial T, or you can do CV is partial internal energy by partial T at constant V. And internal energy itself for canonical ensemble is minus partial ln Q by partial beta. So let's work through this. Let's calculate E bar. E bar is minus partial ln Q by partial beta. So we go to equation 4 and we differentiate it with respect to beta. This one is going to be easy. It's just a linear differentiation. This one will have a bit of trouble because it is log of a function of beta, right? So that's what I'm going to write down. So this becomes minus 0 to infinity g of omega h cut omega by 2 plus 0 to infinity d of omega g of omega h cut omega by e to the power beta h cut omega minus 1. Okay. Now we have our expression for E bar. We need CV. What is CV? CV is partial E bar by partial T. But what we have really hanging over here is beta, right? So this can be changed into partial E bar over partial beta, and you are left with minus K beta square, right? At constant volume. This is what we are going to work with. So you can take, let's call this equation number 5. Use definition of CV in 5. What we need to do is to differentiate this thing with respect to beta. When you differentiate equation 5 with respect to beta, this one has no beta dependence left. This one has beta dependence left. So we've just worked through that one, and you can see it has beta dependence in the form of 1 over e to the power beta h cut omega minus 1. So it becomes CV is equal to K 0 to infinity d omega e to the power beta h cut omega by e to the power beta h cut omega minus 1 whole square beta h cut omega whole square g of omega. Equation 6. This is still valid in general. This is a really powerful equation. We have made absolutely no assumptions about what g of omega might be, okay? So this is super general. Okay, so let's work from here. Now we will use the expression for in 6. We use 1, which is Debye's expression, okay? So we do that. What do we get? We get CV is equal to K. And now instead of 0 to infinity, it will be 0 to omega t, d omega, e to the power beta h cut omega by e to the power beta h cut omega minus 1 whole square, b to the power h cut omega square, and 3v omega square by 2 pi square cs cube. More and more horrible algebra, but that's what it is. Equation 7. Let's use this beta h cut omega shows up again and again. Let's call it x. X is defined as beta h cut omega. With this, we get CV in equation 7 is equal to K 3v by 2 pi square speed of sound beta h cut. And so I'm writing down the algebra because if we really went through every step of the algebra right now, we will be here for a very, very long time. You can go and work through it, but there is nothing profound here. It's just converting the algebra from one equation to another. So, but now pay attention. This x means this becomes e to the power x, right? So we get e to the power x by e to the power x minus 1 whole square multiplied by x to the power 4 dx. So we have something now which looks interesting, and we can simplify it one step further and write this as 3nk, k is Boltzmann constant, 3 by beta h cut omega d by whole cube integral 0 beta h cut omega d e to the power x, x to the power 4 by e to the power x minus 1 whole square dx. This is equation 9. Okay. Let's continue from here.
So how did the omega d come in the denominator? Was
Because
that
we
different?
have, it came from somewhere because we have changed omega to x. The integral variable has changed. That's why. It's the limit, right? It's just algebra, trust me. You'll see. So if you work through everything, write it down explicitly. Normally, I give this as a homework problem. The students slog through the algebra, but I thought I would work through it. So yeah, it's because you have changed the integral variable from omega to x. And also, don't worry about the omega d in the denominator. What matters more in the denominator is this beta term. All the other stuff, 3nk, omega d, these are all prefactors, right? So we are not going to worry too much about it. Okay. So this equation, I'm going to write it down again on the next page. CV is equal to 3nk 3 by beta h cut omega d whole cube 0 to beta h cut omega d e to the power x, x to the power 4 dx by e to the power x minus 1 whole square contains our answer, but this is horrible. If I asked you to just look at it and tell me what is the dependence of CV on beta, you won't be able to do it. If the integral term was not there, if this term was not there, then you can see that CV is proportional to T cube. But we know that's good. That looks promising. So at low temperature, we expect that the integral must be going to 1 or something constant. So we get our T cube dependence that I have been promising. But let's work through it. So we are going to call this as 3nk some function, Debye function, fd, that we have just introduced, which depends on, so this is Debye function, which depends on theta d by t. So I'm introducing more symbols here. In this, we have defined fd, Debye function, fd of y is defined as 3 by y cube integral 0 to y e to the power x, x to the power 4 by e to the power x minus 1 whole square multiplied by dx. And k theta d is the same as h cut omega d. So if you have a frequency, then h cut omega d corresponds to the energy in that frequency. And k theta d sorts of gives us the k temperature. Theta d gives us the temperature associated with that frequency. Okay, so, and this is equation number 9 together. So we have equation number 9. Now we need to take the limits and see it gives us the right behavior. Almost there. So first we will consider very high temperature, temperature much more than theta d. In this limit, you can show that and I'm leaving the algebra here. This will be a homework problem in homework 3. So you can finish through all the steps here and make sure it's okay. It won't be hard. So one can show that FD of theta d by t tends to 1. So as this happens, as FD of theta d by t tends to 1, which means in this expression, the one for CV, this term tends to 1. Or CV tends to 3nk. So we recover the classical harmonic oscillator limit as temperature tends to infinity, much higher value. As temperature tends to theta, much smaller than theta d, then what are we left with? Then we can see our expression. We have to deal with it a bit more carefully. It will be C 3nk 3 by theta d by t whole cube multiplied by 0 to infinity e to the power x, x to the power 4 dx by e to the power x minus 1 whole cube. This part is actually the easier part, the t less than theta d part, because why is this easier? In the first case, you actually have to take the limit of the function and show that it goes to 1. But in this case, I have not done any limit. This part is straightforward. I'm just left with something. As long as this thing does not blow up, as long as this thing does not diverge, it takes some constant value, I have my t cube dependence that comes out. Has anyone seen this integral before? You can look it up. Its value is quite neat. It is, Lewis has seen it, that's good. Its value is pi to the power 4 by 15, which is kind of interesting. You can work through it, derive it. It comes out to be pi to the power 4 by 15. So that gives us CV is equal to 3nk pi to the power 4 by 15, 3 by theta d cube, whatever. These are all constants. But the most important thing, we get our t cube dependence. Okay, so we just showed that Debye's formula actually does work. I left a couple of algebra steps for you, but it does work out. It does give the temperature dependence. And if the algebra steps that I left came after equation 9, already in equation 9, you can see the 1 over t cube term was coming out already, and we were just left with a corresponding integral next to it. Any questions about this? Okay. Good. Let's talk about the midterm for just a bit. And then I will get to the next topic. Let me open it. Okay. You're still seeing Pakoda, right? No, now you see the midterm. Good. So, okay. So this is the midterm. It has one fake problem. If you're submitting a printed copy, just make sure to staple it. And if you're submitting something by Slack, make sure to put your name on the top. Otherwise, information gets lost and my life becomes complicated. So it has several questions. In fact, it has a total of 7 questions. The exam is a total of 110 points. You will be scored on 100. So effectively, you have the possibility of scoring 110 out of 100 if you do everything. If you do that, it will compensate if you don't do well in homework or anything like that, or in the final. So I call the 7th problem as a bonus problem. Oftentimes students just don't attempt a bonus problem. That's a bad idea. Please try it. I will give you some points for trying. It's not that hard anyway. The exam is out now. It is due 4 p.m. Friday. You can send it to me by Slack, or you can drop it off in my mailbox in IPST. Last time, some people delayed their homeworks slightly after 4 p.m. This time, it's going to be strict. You have to submit by 4 p.m. period. There is no delay. So you have Wednesday, Thursday, Friday, more than 3 days to do it. It should not take more than 2.5 to 3 hours. And some problems I had already mentioned in class that they will be coming. Some are not very hard. Some will require you to think a little bit. And many problems have different parts. Of course, some of the parts depend on the previous parts. So be careful in working through that. And you can use books, internet, ChatGPT, Bard, whatever you want to use. So talking to an AI is okay. Talking to a human is not okay. It's a bit strange policy. I've probably never seen it before. So if you're asking any tool on the internet or anywhere to help you with your problem, I'm fine with that. But you cannot have a discussion with your classmate, with your family member, with a lab member. No, that is not allowed. And that's an honor code. Please try to follow it yourself. Any questions about this?
I have a
So
question.
the deadline
Go
is
ahead.
written as 4 p.m. Friday,
Yeah.
but March 15th is written, which is a Saturday. So,
Well, it's Friday. I will change it. Don't worry. It's Friday.
okay.
Yeah, it's March
I have a
15th.
question.
Sorry, March 14th. Yeah, go ahead.
So for the bonus question, it talks about the canonical energy distribution. Is that like the probability of finding the state or finding the system with that particular energy?
I'll leave that for you.
Okay.
Yeah.
Oh, you have to mute yourself. Sorry about that. I'm sitting
No
here with
problem.
Max, but
Mhm.
I had a question. If we were to do something wrong in one of the first parts of the problem, would that propagate to the later parts where we would get-
Absolutely. Absolutely. It will be a disaster.
Okay, so we should really
Yep.
try
Yep.
first, right? Okay, thank you.
Yep. Yep. It's kind of like life, Don't screw up. Now, in life, you can screw up and it will still be fine. Here, you have to be careful. Not all problems are like that. Some of them are. So you have to be very, very careful. That said, if you totally get stuck in first part, does not mean don't try the later parts.
Okay, thank you.
Okay, that does not mean don't try. Okay, and the exam is due on, yeah, sorry about that error. I will put it on Slack anyway. Okay, good. Any more questions? It's easy. You'll have fun, especially since I'm allowing you to use ChatGPT and things like that. You will be, if you find an error in the numerator or things like that, you think about it yourself. I'll leave it to you. And some things are intentional, like, is it factorial of 2n? Is it 2 multiplied by n factorial? Well, think about it. Okay. I want to start the next topic. I want to start it so you can read up on it if you're interested, but I won't go more than 5 minutes. I'm just going to stop here. And what I'm doing now, I will resume from here when we start after spring break. So we just finished application 1, which is phonon gas and related heat capacity. How did we do it? We assume atoms, the gas is made up of atoms which are vibrating in different directions. We first assumed that the vibrations are sort of small. We assumed a classical harmonic oscillator, and we got that the heat capacity does not depend on temperature. Then we said, well, classical mechanics will always have a heat capacity at 0 temperature also. You need quantum mechanics, you need quantization of energies for heat capacity to disappear. So we used a quantum harmonic oscillator where the energies were quantized. We used those values. We looked at the energy in every microstate. We wrote down the partition function. We did it in terms of density of states of the frequency. We worked through how it looks for the Debye density. For Einstein density, we did not work through it. There you would have gotten, instead of T cube, you would have gotten exponential to the power minus temperature, something like that. Yeah, go ahead.
I was wondering, so what is the conceptual problem with having a finite heat capacity at 0 temperature?
There is no problem. It's not what people measured. When people
okay,
measure
so
heat temperature, yeah, it was a measurement, in the end,
okay, so it just doesn't do that.
It just doesn't happen, when people found that you decrease the temperature, heat capacity drops down. You decrease it more, it drops down more. You decrease it more, it drops down more, and it drops down as T to the power cube. This was an observation which had been made long, long ago. This is what we had to. What happens at exactly 0 Kelvin? Who knows? That I don't know. You also run into all sorts of measurement errors and things like that. But big story is heat capacity keeps going to smaller and smaller values as temperature decreases. So this was phonon. This was our first application. Our second application is quite interesting, or as interesting or more interesting, depends on you. Application number 2, we will be studying a gas of photons. This is also known as black body radiation. What is black body radiation? You take a box and you suck out all the molecules out of this. So you make a cavity. Make a cavity in a large piece of material. Evacuate the cavity. And the cavity is going to have some volume V. Heat the material from outside, you are heating it. To a temperature T until thermal equilibrium is established, and leave a very, very tiny void through which you can kind of see it's the tiniest possible void that you can have in the system. Let me write it in cleaner handwriting. Tiny void to see what's going on inside. So what will happen in this case is that atoms of the wall, so the walls of the cavity from inside, atoms of the wall of the cavity will be constantly absorbing and emitting radiation. And the question we seek to ask is, how does the energy density, so you will have radiation at different values of omega, right? Radiation will have some frequency, just like we saw in the previous problem. There is a G of omega. Here also you have a distribution of frequencies that the radiation that is being emitted from the boxes, boundaries of the box will have. And let's say you can measure the energy carried by radiation at a certain frequency. That is known as the energy density of radiation, U of omega. Depend on temperature T. This is the question we are seeking to ask. This is a fundamental problem. This is perhaps, it's hard to compare, but it's perhaps even more fundamental than the heat capacity problem. One example of such a setup is the early universe, and people were able to study that people were able to collect radiation coming from the early universe. There was a big experiment that was carried out for this, which is known as COBE, Cosmic Background Exploration Experiment. And from COBE, they found that if you sum up U of omega d omega, which is the energy per volume over any frequency, energy per volume over any frequency, which is U of omega d of omega, this has a relation that depends as T to the power 4. It is proportional to T to the power 4. We will calculate after spring break, the exact proportionality constant, which turns out to be pi square kb to the power 4, 15 h cut cube, and speed of light cube. This has a name. This is known as Stefan Boltzmann law. And when people did this measurement on the radiation they were getting from the early universe, they were able to fit this super well and calculate the temperature of the early universe. It was, of course, very cold, and they were able to get the value of the early universe temperature using this expression, which we are going to derive using the type of things we have done. It's super fascinating. And in, I think it was 60s, maybe 50s, 60s to 70s, something like that. There were two scientists, Penzias and Wilson. They were trying to do this experiment. They had designed a big antenna. And from this antenna, they were trying to do some experiment on this antenna. They were not quite ready that there might be radiation coming from the early universe. So on this antenna, they would always be getting some sort of buzz. Even though they cleaned it, they isolated it, they did everything nice, they would keep getting some sort of buzz. So they became very sad. They thought something strange is going on. They thought maybe there is a bird. I don't know how to draw a bird. They thought maybe there are birds in the sky, pigeons or something, who are taking a shit on the antenna. And they found some shit on the antenna from pigeons. So they went and cleaned up everything, and still the radiation survived. That's when it hit them that there is something fundamental about this universe. This radiation, it is coming from the early universe, and there is no way they can get rid of it. And that's it's a big experiment. You can go and read up on it. This is what we are going to do next time. And just to connect the dots, application 1, the idea was that lattice vibrations are quantized and they lead to phonons. In application 2, the idea is that electromagnetic vibrations are quantized and they lead to photons. Photons will also have the same energy, n plus half h cut omega. One thing to keep in mind, and you can mull over this during spring break, and this is where we will resume next time, that walls are constantly emitting and absorbing photons. We cannot control the number of photons. In other words, the chemical potential of photons is 0. And I will prove this a bit more carefully next time when we meet. You should remember to ask me to prove this. We will prove this next time, why this turns out to be the case. I will give you some more intuition. So when we solve this problem, we can either work with grand canonical, where we set mu is equal to 0, keep our volume, keep our temperature. What we will find is more convenient for this problem is to work with Q of V comma T, because N is arbitrary. So we just ignore N completely. And we work with an ensemble arbitrary that looks like Q of V comma T. So next time we will write down Q of V comma T, which will be summing over all microstates using the value of microstate energy in every microstate, and just work through it. And we will get Planck's distribution and Stefan-Boltzmann law and all those things. Good, that's it I have for now. So your midterm is out. Once again, it is due on Friday, 4 p.m. Sorry about that. And Samyak, thanks for pointing that out. Any final questions? Okay, so enjoy the midterm. If you have any clarification questions, ask to me on Slack. Most likely I will be completely unhelpful. I'll be like, it is obvious. But every once in a while, you pick up something which is quite useful. And if I answer to you, I will probably answer to everyone in the classroom. You still should ask me through DM. And either I will tell you, make your assumptions, or it's good. Or if there is a serious typo, then I will announce it on Slack general channel. Okay, so see you all later. Good luck with the exam.